Yeah, so I was asked here to talk about Rex computing. As Andy was saying, we've developed a new processor architecture, so a whole new instruction sets, core design, full chip implementing those cores, and with a team of 4 people, which you can see here. So myself, Paul in the Georgia Tech shirt, sorry for being here at Stanford. At least it's not like MIT, I am. But, and then Nariman, who's also in the audience, and Piyush. And without all of them, obviously, I would not be here today. A little over 3 years ago, this just started off as a crazy idea, and coupled with, being a bit young and the naivety of both Paul and I, we actually thought we can make a processor for, basically no money, and, the two of us had to double the team size, but I think we've done pretty well so far. So when we started Rex, we were trying to think about, what are the basic precepts of computer architecture that haven't really been rethought over the past 30 or 40 years. And as we were digging deeper into, what are the really bare minimum things necessary to do computation, we started thinking that it's not as much of the computation itself that is the issue, but how we actually get data to the processor and really the whole memory system. And while there has been a lot of talk about the memory system at a more focus on the memory itself, so trying to find alternatives to DRAM, et cetera, there hasn't been much thought in terms of, how it's actually architected on the chip itself.
Your slide says confidential. I will have to leave the room if that's true.
Excuse me, I've taken a bunch of these slides from other decks, and all of this is not confidential.
Maybe we could raise the screen 6 inches.
Does it still have 2016 on it? Yeah. You can tell how we've been busy actually working on the chip instead of the slide decks.
That's a good thing. It means you didn't finish the whole thing this afternoon.
Yeah, so basically what we were looking at in terms of the memory system was the on-chip cache hierarchy. And over the decades, this has grown from having an off-chip SRAM-backed cache, very small, still relatively high latency compared to the actual chip speed, but still faster, closer access than DRAM. And since the 286, we've gone having on-chip caches, L1, L2, L3, et cetera, without much thought of the implications that has as we start to approach the twilight phase of Moore's law. And so while 30 years ago, if you were looking at this diagram then compared to now, which this is for Intel Sandy Bridge architecture, while doing the actual double precision floating point operation only takes about 100 picojoules, actually moving the 64 bits necessary all the way from DRAM to your register file takes about 40x more energy than that. And that's kind of a problem. And while there's been, all of the free benefits of Moore's law has been really helping that what is now 100 picojoules hasn't really helped much on the other side. So when most people look at this slide and say, oh, well, that makes sense. The DRAM is, separate on the motherboard. You have to, that is having to be refreshed. It's using a good amount of power itself. That's fine. But in reality, about 60% of that 4,200 picojoules is being used on the processor itself. So the DRAM and everything, even if that gets closer to your processor, like we're trying to do 3D integration within packages, and even if we're trying all these new fancy, memory technologies outside the chip, that's only improving 40% of that number. And the main thing that's just happened over these decades is this more and more, adding more and more complexity to the on-chip cache hierarchy in order to try to help programmers is the main point. Programmers don't want to manage memory. Like the initial purpose of caches, just so the programmer can, just deal with the virtual address space, don't have to, segment that themselves, really just make their lives easier. And this idea is is great in theory, but the cost that we're starting to pay, especially as we're not getting the free improvements that we have in the past, is really starting to bite us. So we started Rex with this realization, and said that we need to architect a new architecture, with this fact in mind. So we've developed the Neo processor architecture. So it's a it's a many core MIMD core VLIW. I'll get back to that in a second. Hopefully, people don't get too scared about the VLIW word, with the fancy two-dimensional network on chip, and the big differentiator. What I just spent the past couple minutes talking about is really the on-chip cache hierarchy differences. So we've moved to a purely software-managed memory system where we have just plain physically addressed local memories for each one of our cores, and then do all of the fancy things that are handled by today's hardware-managed memory systems instead in software. And the real goal of this, set off that unless we can really get an order of magnitude energy efficiency improvements, there's no real point in doing what we're trying to do. We're up against enough competition, 4 guys versus Intel, and we have to have a real sort of advantage for that. So as I said before, we've designed a lot of aspects of this, so everything from the instruction set to the full chip. But we realize that we can't just, even though I'm in love with the hardware aspects, you actually need to have software run on this thing, and have this available to folks in a way that they can actually use. And so not just defining the instruction set, core, chip, but also the actual reference node designs and the software tools to be able to use this. So as Andy said a bit earlier about the original S1 team and developing all of the tools necessary for that computer, we've taken a fairly similar approach. I guess we've been able to leverage the past 30 years of advancement and knowledge in that sense, plus the advent of the real development of the open source software community. But starting to do all of this for ourselves is quite a big leap. So kind of give you a little bit of an idea of the instruction set. I guess this slide is maybe a bit out of order from what I originally wanted, but it's a very RISC-inspired architecture. I did say the VLIW word a bit earlier, which few shocked expressions on people's faces. But our real point here is to keep a very simple, very clean design, and try to exploit as much instruction level parallelism, task level parallelism, and actual data parallelism as possible. Everything's load store based, so our memory actually moving data around on chip through multiple chips and using off chip memories is a very simple, clean design, and we've really focused on floating point performance. So everyone's scared about VLIW, and this is the thing I get all the time, with the number one thing being Itanium. So wasn't it proven that VLIW just doesn't work with Itanium? And I bring up this picture of block diagram of the Itanium architecture, and big problem. The original concept of VLIW, which was really pioneered by floating point systems, and the actual VLIW name with multi-flow and others in the mid-late 80s, was this concept that you can remove a lot of complexity out of the chip design itself in order to have a software be able to take some of that burden off. And most of that back then was related to the instruction decoder. So instead of having these really complex CISC instructions, that you had a big fancy decoder that handled all the scheduling, making sure that you're not having any instructions conflict, et cetera, et cetera. And it was the compiler's job to actually do all of that for the hardware. And so when I look at Itanium with branch prediction, these caches, which are indeterminate pipelines, depending on what instructions you're running, in what order, et cetera, where you just cannot actually know how the processor will perform at runtime. When you're compiling an application, how is the compiler actually able to do this and actually make any of these sort of optimizations? So the big part, which I'll get to in a bit with Rex, is this fact that we are really focused on hard real-time determinism for everything. And then the second thing I always get is for Scratchpads. So this concept of a software-managed memory system where we have, just physical addressing, none of the fancy caching, et cetera, for the actual end user, always brings up comparisons to Cell. So if you're familiar with the Cell processor, made as a collaboration between Toshiba, Sony, and IBM, primarily used in the PlayStation 3. It was notoriously difficult to program with because the real idea by Sony and Toshiba at that point was to use what were the Cell special processing units, the SPUs or SPs, and the whole design point of this was they were relatively powerful but still small. They had 8 of these in a 2005 processor, but IBM's part of the agreement was that they were going to be fabricating the chip, but also they want to actually have more skin in the game and put in that power processing unit, so power PC architecture. And the big problem with this was that created a huge bottleneck where in the with the SPUs, the actual only way that you could get to external memory was actually having to go through the power processing unit. So there was this huge overhead, and that system had its own cache, et cetera, that just made it impossible for a compiler to actually know how to access large parts of memory, and just real pain in the ass. So when we're going into the Neo architecture a bit, I like using this as give an idea of the instruction set. So here we have up in the upper left-hand corner, the floating point unit and its instructions. So we've got 22 instructions total for the floating point unit that supports full IEEE 64-bit. In the future, doing packed single precision, potentially half, and other formats. The real philosophy behind VLIW is being able to exploit task-level or instruction-level parallelism. So we want to be able to use the FPU, the load store unit, the outbox or secondary load store unit, and the ALU all at once. So one of the really unique things that we did with our instruction set architecture was this fact that we can, if you look at this full 64-bit word, we're fitting 4 different instructions from 4 different units in it. And depending on the actual register usage of the different instructions, the length of the way that the entire 64 bits is allocated tells you exactly what instructions you can use. So our instruction decode logic is ridiculously simple because we're able to pass the same 64-bit instruction across all of our through all of our stages for all of our instruction units, and each execution unit is able to figure out exactly what it has to do for that. And unlike a lot of architectures, both due to having a lot of register ports, but also the format of the instructions themselves, is that we can actually do things like an FMA to 128-bit load store operations and any of your basic ALU instructions all simultaneously. So in a lot of cases where it's just impossible in most architecture, in even VLIW architectures of the past, where you just cannot really get theoretical peak performance because it's impossible to use all of the execution units. In a vast majority of the applications that we're targeting, that is actually possible.
So, quick question:
Yeah.
Since you just mentioned your compiler in the slide before, I don't know which language you're doing. Are you going to be comparing your compiler to the Bulldog compiler?
You mean in terms of the actual scheduling capabilities, or
just a little more detail.
kind of? So I won't be in this presentation. So a lot of we could talk a bit more later. A lot of our so I guess since we're leveraging so much of the software capabilities to actually make people be able to use our processor. The software really is the secret sauce when it comes to most of this. Very simplified hardware with software taking the role. So we're happy to start showing hardware now. Still going to be a little bit until we show the internals of some of the software. But yeah, the main point of this is we can actually utilize all of our functional units simultaneously and be able to get, at a single core level, to start off with, close to theoretical peak performance. So here's a diagram of our core. We have a 64-bit ALU, a 64-bit floating point unit, and 2 load store units, which are both capable of either half-word 32-bit word, 64-bit, or double word 128-bit operations every single cycle. All of them are fully pipelined, with the only instructions not pipelined is the integer divide. Not fully pipelined is the floating point divide and floating point square root, but other than that, you can issue a new instruction every single cycle for each one of these units. So we can really exploit, get very high IPC count over this. The big point of this is that we can, within a core, if your program fits inside of our Scratchpad, with this current test silicon, 64 kilobytes of Scratchpad, in the future 128, 256-bit kilobyte or more, you're going to hit theoretical peak performance. Like, we can guarantee if you're able to do a fuse multiply add every single cycle as part of the inner loop of your program, you will be hitting 2 gigaflops with our 1 gigahertz nominal clock speed. It's also really small, so not including the Scratchpad. So just looking at the Neo core and actually the router as well, it's less than 0.1 square millimeters in TSMC's 28 nanometer process. So a ridiculously small core size, and I'll have a comparison a bit later on showing how that ranks up against some other both mobile and high performance cores. And what's kind of shown here with the Scratchpad is that it is multi-bank. So we have 8 64-bit single-ported registers. So if you're doing a double word read or write to that, you're actually utilizing 2 of the banks. And we have a really cool hashing system and such that makes that really powerful in terms of being able to, with every single cycle, be able to use all 8 of those banks for both incoming data into the core on the network on chip, which I'll get to on the next slide, sending data out on the network on chip, and doing processing just within the core. So when we go out to the network on chip, so just designing a chip, very simple processor core, and thinking you're just going to have one of those on chip won't really work today, so we're trying to embrace task-level parallelism. So we have a true MIMD model, so each one of our cores is fully independent and all connected to this two-dimensional mesh network on chip. It follows a static priority routing system, so it's fully deadlock free. You're able to send messages every single cycle with 1 cycle per hop for each core that you go down on the NOC. The fully deterministic part is a really important part when it comes to our compiler and actually trying to schedule these things, as just doing something within 1 core is interesting, but actually being able to architect programs to be pipelined over multiple cores, or have completely separate applications that you don't actually want potentially have interactions with other applications on the chip, be able to run and coexist in on a single chip, and so that fully deterministic behavior enables us at the compiler level to actually give hard guarantees on, it's going to take exactly 5 cycles to go from core 0 to core 13, for instance. And with that knowledge, we actually can write very performant and have the compiler generate very performant code. And when it comes to the address space, another cool aspect of architecture is if you look at core 0, that is the first, in the case of our test chip, 64 kilobytes of address space. So address 0 through 64K corresponds to core 0. And if core 0 were to read or write from any one of those addresses, it would be accessing its own Scratchpad in 1 cycle. Now, if it goes 1 address higher, it would now actually be able to write to core 1's Scratchpad. And that's handled completely automatically for it. And if it accesses that address, it takes 1 additional cycle to write out to that. And then that is just 1 additional hop to any core within the chip. This also expands not just to the address space on a single chip, but we can expand the address space to multiple chips, which will be in the next slide. So with this test chip, we've have 16 of our cores and then 2 SerDes. So SerDes on the north that basically routes up to anything below the current chip's address, and chip south, which does the opposite. It's extremely high bandwidth compared to most SerDes, which very good for us when we're considering trying to move a lot of data going through our chip in kind of a systolic array fashion. So 125 gigabits per second in each direction per SerDes. We've been able to utilize a multi-chip module to actually show this off with our current test silicon. And again, that the protocol is actually reutilized for the chip-to-chip links. So over the SerDes, you'd be using the exact same address space if you have multiple of our chips connected, or say are connected to something that has access to larger amount of memory like DRAM. With our current test board, we have the ability to connect to an FPGA which has DRAM attached, and we basically just map that DRAM to be either something higher or lower in the global address space. So to go a bit about the SerDes, since it is pretty interesting. So it's not your traditional SerDes, which is just a differential pair connected to another SerDes following the same standard. But we're actually doing a unique thing using another startup company called Kandou Bus in Switzerland. They've developed a new type of SerDes that is much closer to a source synchronous forwarded link. But so they're able to do this 125 gigabit per second, which is over twice as fast as the bleeding edge new SerDes on 16 nanometer, and we're doing it on 28. But by utilizing multi-level signaling, we can actually do much lower power and not have to have ridiculously high frequencies. And then the addition of actually doing forwarded clock instead of having embedded clock for each differential pair that we're sending over, we also reduces the power significantly. So to give you a bit of idea of how that's connected, on the left here, basically the 16 wires that are abbreviated there, but is the going between 2 of our chips, say within a multi-chip module, or one of our chips and the FPGA that's able to be connected to it. We're able to get up to 25 gigabits per second. This is simplified a bit with a different reference clock, but with this, we can get down to 1.4 picojoules per bit for transfers. And if you know anything about today's SerDes, the state-of-the-art ones used for like HMC and PCIe Gen 4 on modern 28 nanometer chips is around 20 to 25 picojoules per bit. So we get a really fast interface and are not using much power. So I guess give a bit of idea on the timeline of how we got this in here. So we closed our original seed financing of $2 million, as Andy brought up earlier, back in July of 2015. We spent a couple months setting up the company, interviewing folks, et cetera, negotiating with IP vendors for standard cell libraries, fabrication, et cetera, and eventually made our 2 hires in November of 2015, all the way through RTL development till eventually taping out in July 20th of 2016. So anniversary of the moon landing. It was a good day. And we finally got our chips back on October 3rd of 2016. And it's been hell with board development between now and then and now. So to give you a bit of idea on kind of the flow that we followed to be able to do this in a very aggressive timeline. So we developed, a full custom core design and, multi-chip module, multi-core chip and multi-chip module with that design in only 6 months. And so we used a full Cadence tool suite. Cadence has been a great partner. Bit of an ad for them here. But we utilized their newest and greatest and best tools for synthesis, place and route, verification, et cetera, along with a really great tool called Joules that I like to highlight for allowing us to actually do early power analysis, and was really, really influential in terms of us being able to make good design decisions to optimize for power, which is really the name of the game for us. We're running on about a weekly flow, going from a new core RTL complete to being able to have full place and routed net list that we were able to do power performance and area analysis on, and eventually from having final chip RTL to having what was supposed to be our final tapeout net list final tapeout GDS that later had to be ECO'd was only a month. So very simple design enabled us to really do things really, really quickly. So kind of to give you a look at what we actually produced. So the 16-core demo, you could see the two SerDes, the north side and the south side, along with our 16 cores. The big, blocks that you see in the middle there are the Scratchpads. So each core has 8 Scratchpad banks. As brought up before, we utilized the ARM standard cell and ARM memory compilers for those. Actually, for this, and where I'll show in a little bit with we were originally targeting about 32 double precision gigaflops per watt, and about 8x better than Intel on a newer process node than what we taped out at. And again, built by a team of 4, and we're expecting to have a newer version next year. This picture on the bottom here is the multi-chip module. So we've got 2 of our 16-core chips with the 125 gigabit in each direction link. And then the links on the external sides are also broken out, which enables us to connect multiple of our packages on the board, which I'll be showing in a little bit. And yeah. So the evaluation kits, here's a picture of the board that I'll be demoing in a bit, as well as we're able to connect this to an FPGA. So on the flip side of that board, we have FMC adapters, which allow us to plug into a variety of FPGAs, as seen here, and enable us to actually really stress the memory bandwidth of our chip. And those will be on sale shortly. A bit on compiler and that fun stuff. We've been leveraging the LLVM open source project. So we created a custom backend and really have been working most on the optimization levels. So most of our focus has been trying to have the compiler be aware of the latencies we have to different locations in memory, it's mostly scheduling issues that to be able to get most of the performance. Right now, there was some tweaks we had to do on the front end to be able to get C and C++ support with Clang. We have very rudimentary support right now, and most of our testing is being done with assembly that we have written through the RTL and now having real silicon development process. And I'll also be giving a demo shortly for our software simulation tools. It's called NeoSim or NeoSim ICAS, the Interactive Cycle Accurate Simulator. With this, we get so we actually were able to generate that using our own RTL. So the exact same RTL that we taped out with, we were able to make a compile to C++ to have a cycle accurate simulator that is pretty darn fast. On our Intel i7 6700K processor, desktop CPU, $350 or so, we're able to actually get about 1 megahertz simulated speed for our single tile simulation, which is really fast compared to RTL simulation. When we were doing most of our work initially with a variety of different RTL-based simulators, we were lucky to be getting maybe 25 to 50 kilohertz. But we get the exact same level of simulation detail. And unlike pretty much any other simulator that you can get from commercial semiconductor vendors, you can see every single register within our chip. And some of the cool features, which sadly aren't working today, I was hoping to show, but we have cool things like a schematic level viewer to be able to see inside the actual pipeline cycle by cycle, being for each of the functional units, and also being able to see things on network on chip, have sort of heat maps based on program runtime. Library support. So this is very much work in progress portion, but is extremely important for our overall future. So we want to be able to support as many of the existing programming models as possible, but obviously we have some preference to a couple of our favorites. But in terms of real application areas that we're looking at are mostly things where you would be running, bare metal code on this. So we really love DSP-like applications, anything, and our first demo that I was going to show here today was for FFT, for mobile base station processing. I already talked a bit about the debugging profiling, but cool thing that LVM, with some of our changes, has been able to give us some really cool graphs in terms of being able to show, similar to the Bulldog compiler originally. Josh Fisher's original Bulldog paper was, is still pretty awesome to me because, you get to see these graphs programs, which most people just don't seem to really conceptualize well. And real-time signal processing, I was just mentioning some of the DSP stuff, and where we see really our best levels of performance and efficiency gain is in the DSP mobile base station space, where with the oncoming 5G evolution of technology coming, there's been a real push by the telecom vendors to utilize FPGAs and more exotic hardware than they have in the past, which actually is hurting them a bit when it comes to power efficiency and cost. So we see ourselves as having a very good solution for that. So I've got a live demo that was working 4 hours ago and then broke 3 hours ago. Yeah. Don't work with animals or do live demos. So I guess, can the camera be tilted at all onto the table? Yeah, right here. I can't see too well, but this is our development board. So on that picture, not that one, this one over here, I guess. Yeah, here. Cool. You can see it, we cannot. All right. Yeah, it's showing up on the screens behind you. That helps. Oh, well. There's not too much on it. I guess there's like the Cylon Knight Rider eye, which, I'm a fan of. But so we've got a development board, have the Knight Rider kit sort of thing going on there. And we have slots for 2 of our packages. So we can have up to 4 of our 16-core dies, total of 64 cores on a single board. Right now, we only have a single package in there. I don't want to open that up yet, but I guess I could show you. Here are the chips that would go in there. Yeah, the live demo I was going to give was a 1024-point FFT, so good. We're using it as a benchmark to doing a 10 megahertz, 600 subchannel FFT baseband for LTE. And I do have some numbers, but I'm just going to see if this works. So if we can switch the computer screen. So, don't think it's, there we go. Cool. So here is all the commands that we have on the board. So we've got a PIC microcontroller here connected through UART to my PC that actually is connected to our debug SPI interface on our chip. We've got a bunch of fun commands on here, but sadly it seems that I broke the chip earlier. So I'll try doing, this just initializes the ADC and gives us our initial values for actually being able to do power measurements and everything. I can do power. And right now, domain A, which is our chip, is using 11 milliwatts, which is a bit too low. It should be around 50 just idling right now. I think that in doing a stress test earlier of this, I left the FFT running for about an hour and a half, and after I rebooted it, it was dead, or was now exhibiting this issue. So I can just turn on the PLL. I'll set it just to do 500 megahertz. Right now I have 750 and 1 gigahertz supported as well. And I'll do a FFT and do it for chip 0. So it's executing, or it's sending the code over. Takes about a minute or so. But oops. Or it may have died. Actually, so we're doing full 1024 points. So we're using 2 banks at 8, so it's total 16 kilobytes of data onto all 16 cores. So this is going over SPI. Due to a board issue, we actually are not able to use the hardware SPIs on the microcontroller, so we're doing bit banging, so it's a bit slower than you would normally expect. Huh. Okay, it gave me back to the terminal, so it may have ran. Let's do power to see what the power is. 32 milliwatts, yeah, it does not seem to be working. But anyways, we do have cool commands like read CSR, so I can do help app. I always forget the. So read CSR, we want to do it to tile 00 on chip 0. Or I want to do CSR 11, which is the program counter. And I'll do that for chip 1. Well, the program counter has a value, so something actually did run there. And that does. I don't think that is actually a valid program counter value. So something is definitely messed up there. But yeah, good thing I did take pictures before it broke. So we just got these chips actually running about 2 weeks ago, and we just got them running about 2 weeks ago. We were running some really basic tests. A couple of the chips that we put on just didn't work, and we didn't know why. So we eventually got one that worked, which this one's been going pretty good for about a week. But anytime we've got any results, I always take pictures. So happy I did this time. So this was before, this was doing the initial power before I even turned on the PLO or anything, and it's about 59, 60 milliwatts for that domain A, which is our core power domain, and then that domain B is the I/O power. It says P0 at the end there. That's just a bug in the code that I didn't bother to fix. But you can actually do the calculation 1.8 volts times the current, which I did a bit later on, so don't have to pull out your calculators. PLL3, set that to 1 gigahertz. That all programmed fine, and the chip got up to about a little under 100 milliwatts. And then eventually here, doesn't let me zoom in too well there. We were doing load FT, so we did see on the screen before that it was executing the SPI commands. It didn't seem to actually getting to loading the FFTs. There's a handshake there that happens. Sometimes, since this is broken for the past 3 hours, it has actually done the handshake, but then it seems to break later on. So still have to do some debugging with that, and eventually actually starts doing the reset, which sets the PC counter back to the program counter back to 0, and then it starts the execution. And in the end, it got the test running, and I did power check, and it was up to about 223 milliwatts. After leaving that on and just keeping it on for about 45 minutes or so, when I checked again, it was up to about 250 milliwatts, and that stayed about constant. So in terms of what should have happened when we did a live demo, but I'll summarize for how it was a bit earlier, we were doing about 1.06 gigaflops per core while running at 1 gigahertz, so 16.96 for the whole chip. The power usage for the actual core power, all of our cores and the PLL, was about 250 milliwatts. Power usage for the I/O was about 178, and while that was not running on the current chip, but if we were fully saturating the 125 gigabits of the SerDes, that would have added about 250 milliwatts. So in total, adding all of those up, even the part that we didn't test today, give us about 25 gigaflops per watt, double precision, so full IEEE 754 2008 64-bit. Many of the numbers you may see, that don't actually say that exactly usually refer to single precision or something that isn't IEEE compatible. So that's about, and this is not fully optimized assembly code right now, and we're still about 2x better than Intel on 14 nanometer today, and that's Intel's advertised numbers, which you're not going to see in reality. So to give you, and that was also for an FFT, which has question.
Yeah, it's pretty clear you have a computational efficiency.
Yeah.
How is it your architecture compared to like Intel in terms of the overhead of like a context switch, right?
Yeah, so I guess that's a longer question to answer. So when it comes to like relocating code, for instance, so one of the cool things about our global address space is that at a, if we have a set of code that is just running on a single chip, or sorry, excuse me, a single core, we can actually move that to any other core without incurring any penalties. There's nothing in the instructions that need to be changed to be moved to different cores. Thing that does, like, since I guess I didn't specify explicitly, but our network on chip is write only. So for instance, when we're, any time that one core needs data from another core, the core that actually has that data needs to send it. So it's the job of compiler, or if we have an interrupt network, which I didn't show explicitly, but it's the job of core to issue an interrupt to another core to say, hey, I need this data, or do some other sort of handshake. We don't, like, the whole sort of threading model that we have for this isn't one that particularly like goes to something where you want to have a core do a switch like that. But the real point is we want to have data in the Scratchpad for its execution when it's actually needed. So we do have things like, we don't have branch prediction, but we do have branch instructions with delay slots, etc. So like in this FFT, we were, a lot of people don't like branch delay slots, but we were able to exploit that to, get a bit tighter inner loop and such. So much longer answer, but so to give you a bit of an idea of comparison for what will be our production chip, 256 core on 16 nanometer, based on what we have right now. For each core, in terms of double precision floating point, we're able to theoretical peak of 2 gigaflops per core. You can multiply it by 256. The numbers from Intel and Gang are pretty much advertised as you are never going to exceed this, rather than what you see in real life. And I can do a whole presentation rant on how things are benchmarked and advertised. But most of the numbers that you see from the big guys, they want to be showing their level 3 BLAs, their dense matrix sort of workloads, since pretty much anything can do pretty well with that without needing to have much in terms of memory bandwidth. And so big architectural decision on our side, both at a single chip, if you're just able to load up and do everything within the memory of your single processor, we are going to hit theoretical peak performance. That we have the bandwidth and the ability to use all the functional units to do that for level 1, 2, and 3 BLAs. The FFT I showed, not super optimized, but doing 53% of theoretical peak is, I think, a pretty good start, and we should be getting much closer to that. Once we actually get real LinPack compiled and running on this, it will be blazing. So we see ourselves being about 10 years ahead of the gang when it comes to energy efficiency at this level. This year, Intel's next generation processors are staying on 14 nanometer for the first time. Moore's law effectively is over in terms of just simple CMOS scaling, and in terms of, since Dennard's law breakdown, etc., we just haven't been seeing the same improvements over the past decade, and it's going to plateau to a greater extent, and I think really realized by everyone over the next decade. But we see ourselves scaling very well. We really like what TSMC has to offer in the next fabrication generations, and we also see there being a ton of architectural improvements to be made. With this test chip, we were very conservative in terms of decisions we made, like our idle power with just the PLL running. Technically, the whole chip is like, program counter is just set to 0, but all the functional units don't have any, fancy clock or power gating or anything. So if we were to really try to leverage doing low power design techniques, our chip, like just their current chip at 28 nanometer, can be competitive with the next couple of generations of Intel. And on a cost semiconductor economics perspective, we're a big fan of keeping to small dies. So while the big, Intel Xeon Phi chip and any of NVIDIA's GPUs are pushing 600, 700 square millimeters, the yield and such for that is very, very low and leads to high costs and, suboptimal kind of designs. You have to account for being able to have a bunch of redundancy in your design, which makes, you have to make sacrifices. We see that like 100 square millimeters as being a real sweet spot in terms of how you can fabricate things and be able to get away with, having very good yield and, make very well optimized designs.
Where did you get the Intel yield number? They usually hold those rather closely.
It's a good guesstimate.
I see.
Yeah, I would. So, in terms of like NVIDIA's yields, like we're sharing, a fab with TSMC. Once you're pushing, 500 plus square millimeter die sizes, your yields start dropping. Yeah, so we got 200 dies back for this test chip, and doing a multi-project wafer like this is not a good way to calculate yield in any way. But we're based on the yield for the same size die that Apple, et cetera, all get with their mobile devices, chips. We expect to be in that range. The thing that the worry the worry I have with that is we have a lot of memory compared. So on the 256 core chip that I'm saying here, we would have 128 kilobytes of SRAM, and when 60+% of our die area is SRAM, we'd rather just throw out the dies that have any SRAM failures and only keep the ones that pass these tests.
Both NAND flash and disks got a sudden jump in capacity when they decided memory can be wrong all the time.
Yeah, I guess I like my stuff being correct.
If you believe in erasure encoding, if every fetch is wrong, you're paying for the circuits anyway, so you might as well have them always active.
It's definitely a thing we want to explore, but there are ECC SRAMs with the 16 nanometer stuff. Like it's an option in the memory compiler to have just single bit correction and like 2 bits detection, or I forget exactly, but it's definitely a popular thing on newer designs. Something that we're willing to explore, but since we have so much SRAM, adding anything like that is going to be a big cost.
A bigger cost.
Excuse me?
Not adding it would be a bigger cost.
Yeah. Well, so far, like when we tested the memory on this test chip, it's surprisingly all worked, and 64 kilobytes in 0.27 square millimeters for the whole core size with the SRAM compared to the 0.1 for just the core and router logic. We were surprised that worked. But give you a bit of an idea in terms of the total area size for different cores. So just compare those on a 28 nanometer process. Obviously, TSMC and Global Foundries are a bit different, but it's a comparison. We're getting significantly higher flops per square millimeter, and like compared to an ARM Cortex A15 core that's 10x larger than our core, we're still significantly higher performance. And then same thing with the full x86 core. Granted, that Jaguar was primarily a mobile device CPU, if I remember correctly, but I'll take it. Same thing with Atom, but the big comparison here is Haswell, which is not only a real Intel high performance core, but one manufactured on a more advanced process node. So 22 nanometer. I love TSMC, but Intel's had the fabrication advantage for a while, and we're still little tiny core punching outside its weight class. We've got some great advisors, also not on here. I'd like to thank Lenore Mullen and Isaac Yonemoto and a bunch of others that have helped us a lot along this whole process. And we've done a lot in a fairly small amount of time. So just a couple pictures, which I forgot I had as hidden slides. So I'll go to show those.
Very nice.
So that's my index finger that you see in the background there, out of focus.
We have ways of verifying if that's true or not.
I'm turning off Touch ID on my iPhone now. That's it's a 3x4 square millimeter full die. It has, you can kind of make out the SerDes on the north versus our core. Obviously, the top metal layer, while it looks pretty under light, it's not can't actually see that much in terms of details. But we have 150 micron bumps on the SerDes, and then higher bump pitches over the main cores, and 240 bumps total. It's not very complicated at all, although we're looking at some really cool micro bump technology around 30-40 microns with advances on TSMC 16 nanometer. So very excited about that. Made this using our GDS2 that we taped out with. Pretty design. I'm really crossing my fingers at some point I'll have a couple hours to etch off some of the upper layers to do another photo like the one before, and actually try to see some of the internal circuitry and such. But yeah, that's pretty much that. We could do a Neo Sim demonstration. We got it ready for the FFT that was supposed to run on the real hardware, so you can now just see it running in simulation. So, Nerman, you want to come up? Cool.
Just while he's setting up.
Yeah.
So what is the memory latency on a load?
So load is 1 cycle.
1 cycle. And remote transfer between cores?
1 cycle per hop. So, going all the way down and across.
It's a log.
Yes.
It's a log mesh, or is it just a log or just mesh?
Just mesh.
Okay.
So when we're going off chip, so for the SerDes, 125 gigabit per second bandwidth, with the latency being 4 cycles from point to point. So when you go off of the router on die 0, appearing on die 1, you're getting, that's an additional 4 cycles.
And the memory accesses are perfectly uniform, no banking or anything like that?
There's banking, but it's all aligned with, so all of our memory addresses are byte aligned, and you can, yeah.
So there's no variation in
No.
strides or anything like that?
No.
Quick question. Is your mesh
Wrapped so that it come.
No, it's not a torus. Would love to do that, but next time.
Question.
Yeah.
One is like parallel numerics, and counter to that is like a sequential convolution, and a good test for that is entropy coding. For example, Hoffman or arithmetic coding.
Mm-hmm.
Do you have some numbers on that? They also map get a measure about regular programs, but the most complex convoluted are the entropy coding. So do you have a number? How many clocks per bin coding?
I don't know specifically for that application. So our compiler tools are still, our main focus for the past 2.5, almost 3 months has just been getting our boards working. So we haven't been able to spend the time that we were originally planning on trying to get more software to run. This FFT that Nariman's about to show is like the first quasi application demo that we've been able to muster and did have running on hardware, not, and now not.
Any test on sequential nature of computation?
Do you have a better answer for that?
For it.
Sequential code,
Yeah, I don't know.
branch intensive code with.
So this one, this is an in-place FFT algorithm. It has 3 for loops in it. A lot of iterations.
Yeah, you can start. You can just start.
Okay. Yeah. So yeah, we easily use the branches. Basically, I'm a hardware engineer myself. I'm not a software engineer here, but I use the assembly, wrote different codes for memory copy, matrix multiplication, and the FFT, and it was just very basically efficient. We use the branch delay slots, and we can parallelize basically instructions.
I think the question is on serial code, like compress out of the spec benchmarks. That's a particularly tough one for a VLIW. You haven't looked at any of those?
Not yet.
Case in point, Intel gave up on it already, and so did NVIDIA. I know it because I was contracted to design our alternate sequential architecture. So, but there are ways how you can map that sequential to entropy coding into parallel architectures.
Okay. I'd like to talk to you more about that.
I actually was on the HP team that transferred Titanium to Intel, and I coded decompress and got nearly 6 instructions per cycles. You can do it, but it's hard work.
I got 3 bins per cycle. That's like there are several IEEE things on that. But Intel's, it is in the generation 6 Intel's processor, but their main interest is different. So maybe we can talk on that, how you can utilize that approach.
Yeah. So right now, in terms of what Naren's about to show at the simulator, we're able to get cycle counts for things and such, but it's still a relatively very low level development environment for us. So we're hoping that we'll be able to get more real applications running once we have the hardware in a more stable state. So I guess I could talk through it. So this is ICAS. So not very pretty at the moment, but functional. So we have basic scripting interface. You could technically load that script into the thing, but create one of our tiles. Yeah, you can go through it.
So yeah, first we add. It depends how many processors we want to, how many cores we want to run. For example, we have 16 cores. In here, we are just using one of them, and that is tile number 0. In the simulator, we add the tile first, and then we start initialize it with the initial code that we have. Like we set the program counter to 0 and some other operations like rounding. We set the rounding type and those kind of stuff for the floating point. After the reset, with this command, we load the assembly code that I have written before. For example, this is an assembly code for FFT. It's not optimized at all, and it's basically, it was written in 2 days ago and not optimized at all, and basically, but
We also had a power outage.
Basically. Well, we work on this more later, but this is just for a demo that we can show that we can do this FFT on our core. And so we have the FFT assembly, I have the 3D factors for the FFT needed, and I have the inputs for the FFT, which are 1024 13-point double precision values. So if you go to the script, after the loading,
Thank you. Oh, okay.
okay. So Yeah, and after we load the program into the basically this simulation environment, it takes for this one actually it takes about 100 cycles to load more than 100 cycles. We load it into the memory to the basically tile, and then after that we start the execution of the code. So what I can show you, I usually just copy and paste the whole thing. So basically what we do here. It will, to this point, it will initialize the Scratchpad or our memory. For example, I can show that I have loaded the X values into the bank number 4, starting address 0. I can show maximum for now. Okay, I can show, it goes up to 8. I can show 5 of them. So you can see the X values in this basically memory addresses. These are the IEEE format. And then, so now we can see the Scratchpad memory values. So what I did last night, after running the FFT, I can compare the output values in the Scratchpad with what we expect, and they were correct. So the FFT was working, but to see how and so this basically column shows the Scratchpad values, which is our memory. This one we can see the register file values and our CSR registers, which we use to program the core. And then these are the GRF and FRF basically.
General purpose register file and floating point register file.
Right. So I can actually start. This is cycle accurate. If I say step 10, basically it will do 10 execution of 10 instructions and
10 cycles.
10 cycles, and then basically whatever changes, the simulator basically shows it in a different color. And this one, this plus one, increments by 1 cycle basically. And well, this FFT takes a few 100,000 cycles. For example, if I do 100,000 step, it takes a little bit time. And
do you have
then,
the NeoSim console open?
Oh, yeah, it's on the back. This one?
Yeah. So this is, scrolling the wrong direction. Okay, so for example, we did, 100,000 steps, and so it was running at 377 kilohertz. Still, that's, 10x faster than, this is running on Intel Xeon, 2 gigahertz compared to the 4 gigahertz that I mentioned before, but still much faster than regular RTL simulation, but still fully cycle accurate. I guess one other thing I want to point out, that this console that's being showed here is the server for the actual simulator. So this ICAS GUI is able to connect to a external server. In this case, it's just running on the same machine. But one of the things that we want to enable is have simulator instances running up on an external server that has a bunch of cores relatively fast, but be able to have the actual client running on any sort of device. So you have a very can have development tools running anywhere. So continue.
So I can just jump to the basically end of the simulation. Maybe I go 200,000 more cycles, and it's going to finish soon. Okay. Yeah, so when I add any cycle, so we don't see any change in the GRF and FRF values, meaning the execution is done, and then at the end we have a for loop, just to keep the programming counter basically not going to the beginning of the program. And when it's done, we can see the final values in the Scratchpad, and that's how I compare the values with the expected values, and they're correct. And we have added a few functions just in the last 2 days. We don't have to see the values in hex. Now we can show the values in decimal, and basically it will be easier to interpret them.
Yeah, that's basically it. Thanks. So that's the basics of the ICAST tool. There's our assembler, and so like the assembly file you saw there. The actual machine code, obviously, that's being generated by LVM, currently with just a very basic set of optimization passes. But the actually taking from C code, probably take me a couple minutes to find it, but we do have.
So those no ops, that's the add latency that you're waiting for the result?
Yeah, so this is really just not optimized at all, but yeah, since it's pipelined, we're just waiting for that. There's a couple of examples in here where you're having multiple instructions on a single line, but like, for example, all of these, like this, here. So this has 2 instructions together, but there's multiple cases here, like with adds. Like this add could have been done up in another spot, but yeah.
So integer add is 4 cycles? Is that what I'm seeing there?
So yeah, to get correct, so to get through the full pipeline till it's back in the register, but you can issue a new one every cycle. Yeah. The only things that are not pipeline are the integer divide. That's you have to wait 67 cycles for, but 3. So the integer divide is 67, but our floating point is only 26. But you can issue a new floating point divide every 14. Huh? 12, okay.
Or it's just simple.
I couldn't hear you.
Are you using SRT divides or is it just subtracts and shifts?
For
Divide.
So the addition, or so the ALU divide is what do you call it? Grade school division, log division.
Yeah.
The floating point unit. Actually, do we ever figure out what they use? So the floating point unit is Berkeley hardfloat.
So yeah, one of the things.
So whatever.
Iteration?
I think they use. I
No,
thought they use
it's
Goldschmidt, or do they use Newton?
No, you're only Goldschmidt, it's not self-corrected.
It is Newton.
It's Newton and correctly rounded?
I believe you were the one that verified.
It verified against whatever.
I've got patents on division. And so I'm the expert on this. Maybe we'll talk after.
Yeah, Goldschmidt, you can if you do a floating point Goldschmidt, you can check at the end and figure out.
Goldschmidt isn't self-correcting, so you have to use full precision all the time.
Could you
You
say
need all
that a
the
way
bits.
to see the information like in the pipeline?
Yeah, so that's schematic view, which is not working at the moment.
So,
If we didn't have the power outage, we would have.
so just to calculate something like A plus B plus C, if I'm understanding correctly, that's 4 or 5 cycles, because you can't use the output of the first A plus B until 4 cycles later?
Yes.
Correct. So I think there's an, so that just for integer addition, correct?
Just like addition. Oh, yeah, integer addition.
Yes.
So a mixed test could be a very common one in video codecs. Is 8x8 2D transform cosine. It doesn't have the sine part, it's just the cosine. How many clocks would that be?
There.
It's a 8-point 2D 8x8 transform, DC cosine transform.
We haven't run cosine yet.
Yeah, this is all questions for Paul, who thought it was better to be programming than to come to a talk.
I see, because those numbers, like mentioned, 6 clocks per bit decode, number, or the one I am proposing, I have solution 3 bins per clock, which is like orders faster, and then is the cosine transform, which is these are very practical use ones. So a comparison you have to compare against is like 12 clocks for one 8x8 2D transform. So if you can beat that, then you're better than Intel. Otherwise, it's confusion a little bit.
Well, I'd like to sit down and talk a bit more. I think I could show you some of our ISA documentation that would probably answer that question better.
They actually use the cosine transform because it has fewer floating point multiplies at the expense of additional integer multiplies. And it was designed at a time when the ratio of those two operations was different. And I've argued they should just be using a full FFT, and it will, on a machine that optimized for floating point, it'll run faster. But they still use the cosine transform. In the
Yeah, I was one of the persons who decided on going the cosine way.
And it was the right decision when it was made. It's not the right decision now.
Now it has gone to integer transform.
Right.
So it stays integers. And this is
Just to be clear, some of these algorithms, you're not running them on a single core, you're running them on 64 cores. So it's tremendous parallelism compared to a 4-core.
Yeah, and I guess one of the things that we have to also look at is just what sort of instruction bundles we can actually put together for some of these things. So
the FFT that you were going to demonstrate, but then that was actually using the spread across all 64 cores?
Yeah, 16. Yeah, but yes.
This one was just on one. This one was just on one.
The simulator was on one. The one that actually hardware was, yeah.
That's when you're kind of benchmarking against. Yeah, that's fair.
John?
Can you talk a little bit about your business model or your plans, how you plan to introduce this to the world? Are you going to become a chip vendor or a board level product vendor or a system level product vendor or an IP licensor, or what do you expect to do?
Cloud service.
Anything but Bitcoin, but so we're mainly looking at being an actual just fabless semi, chip vendor. The main goal in having this development board is part proof of concept, part being able to, with the FPGA, we can hook up this to either a PC and kind of have a coprocessor sort of demonstration, or even better, have it connected to a radio antenna stack. And with that, we can have one FPGA on this side that can be running a soft core or something, running Linux, and you've got 100 gigabit Ethernet in, do a whole bunch of stuff, sending data over to our, say having 4 of our chips, so 64 cores total going across here, and then another FPGA on this side that has the actual LTE radio antennas, and we could be doing full digital software-defined radio on our chip, significantly lower power than anything else out there. So this 1024 FFT, not optimized and missing a lot of pieces, but in terms of the gigaflops number for that, the efficiency for that is very comparable to wanting to do an LTE stack. So we're beating the ASICs and DSPs doing that right now with a fairly hacked together chip.
So the business model is that perhaps someday I'll be able to send you a purchase order and you will send me back a box of packaged discrete chips that I soldered in my boards.
Yes, so mostly it would be for OEMs. So we want to be working with the Ericssons, Nokias, et cetera, of the world for putting these into the boxes for that.
What is the current state of the chip architecture documentation, the instruction set, the instruction encoding, that sort of stuff?
So if we can switch to the other computer, I forgot I wanted to show that. So we have both a web-based and PDF version of the ISA documentation. So the goal is to try to get this out next month. We want to be able to publish this on the website and shortly after have some version of the simulator tools available. But it's currently partially auto-generated, and we're throwing in a bunch of documentation with that to actually inform on the precepts of the architecture. But the main goal is we want to have C support to go along with this sort of release. So there are plenty of people that are going to want to look at the ISA and the actual assembly, toy around with that a bit, and we want to give the tools like ICAST to be able to, so you can really make optimized great assembly. But for most people, you're going to want to write in C or some other LLVM front-end language.
Subject to you getting your documentation so it's intelligible to others, are there non-disclosure issues? Will that be thrown into the public domain?
No,
not public domain, but that'll be available to anyone that's interested.
It's not going to be public domain or open source, so we do have some patents related to the particulars of our instruction set. But
Long term, I'm just saying not under on the NDA.
yeah, we want to give as much documentation just out to the public. Obviously, we're keeping rights, when it comes to actually producing chips with the instruction set, et cetera. But in terms of all the CSRs, exactly, how you can tweak and do everything possible, we want to be as open as we can.
So if there's no floating point operations, those slots are just left empty, or can you put integer in them?
So here's taking a look at the ISA a bit. So you're saying for this whole slot here?
Yeah, I'm just doing purely integer computation.
So those would all just be zeros. In the future, we've been thinking about some ways to be able to refurbish some of that.
One of the surprises on the Intel was more interested in scalar code than high-performance computing. And so they insisted that they have different instruction formats, both with floating point, and they added additional integer functional units so that they could keep the slots busy. And that was one of the changes that came from the HP version to the Intel version.
Yeah, one of the things I'm going to be working is refactoring this spreadsheet sort of thing to be a bit more readable, usable. But there are some really powerful things you could do to really optimize. Like if you want to do a fuse multiply add up here, and you need to have this third operand register, but you also want to be doing a post modify 128-bit double word and do that on both units, etc. Well, it may look like, oh, these overlap. You can't use this instruction. When in reality, you could just have the same register number. This is using floating point register, that may be using a different one, etc.
So you might be able to dual purpose the floating point functional unit to do integer ops.
Yeah, so that won't be able to be done with this silicon, but in the future, yeah. There's a lot to be learned in terms of exactly what packets of instructions using the full 64 bits to its maximum potential. But the basics of the architecture, the ISA, etc., all of our instructions fit on a single page. You can look at this, print it out, and get a good idea. And in terms of the full ISA documentation, I think you can get a very good idea in a couple hours to maybe an afternoon of looking at our documentation in about a month.
Full disclosure, I've had the occasion to chat with you several times through the last couple of years, and I don't claim to understand your architecture issues, but I've been surprised at how well you seem to understand a lot of different architectures from a lot of different vendors, going back decades. And I've got a 40-year head start on you, and you know a lot of these products better than I do. So I'm wondering what got you interested in this field of architecture, how long you've been trying to study all of these competing products, how you managed to learn things from them, just how intimately familiar are you with using all of these things that you've alluded to. You had Itanium and x86 and some other architectures up there.
I've used most things that most common things that have existed in the past 20 years or so my lifetime, I guess alpha and after, but like a lot of the floating point system designs, multi-flow, et cetera, that we've taken a lot of architectural inspiration from. CDC, everything back to the CDC 6600. I'm a huge fan of and love, but sadly I've not gotten the chance to use them. And in terms of emulators and such, if I had free time or something, that's something that I would love to do because of, but in terms of actually being able to create those emulators, since I haven't looked deeply, but the few that I've seen don't seem to be that great. But in a general sense, just to say how I got interested in all this, I started getting more interested in deeper aspects of computer science when I was about 13, and I just always had to know why something, not just the how something works, but why that developed. The whole reason Rex exists and we went in this direction was not just the fact that I could not just accept that the way something is done is the only way it can be done, and that it is necessarily the right way. So
That's for sure.
I haven't seen anything about any kind of privileged mode or the kinds of things that float around in most of the big CPUs that are floating around these days.
Yeah, so
Go ahead. I think you're going to answer my question.
Okay, so there is no privilege mode or anything. We are looking at having a bit of memory protection options, but at it's more like address protection, like ranging at the network on chip level in the future. There's a lot of things that we can do in terms of being able to say restrict access to certain portions of the network and give a lot of these, not just the level of hard real-time guarantees for latency, but saying there's no chance at all that, stuff can get passed around certain things. So that's not in this silicon, but we've already been toying around with things for the future.
There are applications where it's not needed.
Between using a VLIW instruction set and Scratchpad memory and branch delay slots, it seems like you've got a really big compiler problem on your hands.
Yep.
And 30 plus years of VLIW experience has come up with much better superscalar compilers.
So I think the thing that's just never actually been done, or at the very least done well, is the fact that there's not been an architecture that gives memory guarantees at the level that we do. And the problem I've just looked at time and time again is that if you cannot say, be it because of some particularity of the network on chip or because of where you are in the pipeline, what instructions you executed, whatever, if you can't say when you can use data or where it will be somewhere else to be used, there's no way a compiler can actually figure things out. In our case, we're able to leverage a lot of the basic stuff just from the open source community. There's been tens, hundreds of millions of dollars invested into LLVM and the things surrounding it by Google, Facebook, Apple, etc. We've been able to leverage a lot of that up to now to just get basic support working. And the relatively simple optimization passes, the future parts are actually are difficult in terms of being able to do this. That there's, we don't have a
Parallelization tools that exist for cache memories now aren't going to apply.
So you can utilize our Scratchpads like a cache in a similar way. It's
Without
just
history.
not without history, without the functionality of automatic, like the hardware trying to make a guess.
Yeah.
But in that sense, we're also never going to have a cache miss. It doesn't like not having a hit, but you're not having. So
I think you're going to end up with something that's really fast on certain benchmarks, and it's going to be painful on general purpose.
well, we're not running Windows on it. That's one of the things. But not running Windows, and I think for most of the applications we're looking at, the ones that we've already made small demos for are things, DSP-like tests, which have been the things that have continued to be VLIW through. The scary thing for me a little bit has been TI is now trending to actually using real hardware managed caches, and their efficiency numbers have actually gone down with with the newest generation versus older ones. But
so Paul's going to kill me for getting this wrong, but my understanding is that basically the huge thing is the determinism, right? You know when something is going to happen, and effectively this is this optimization problem has fairly good solutions in good algorithms to find a reasonable solution, even if it's not necessarily the most optimal.
The hard part is the if test where the latencies on the two branches are different, because you don't know at compile time which branch you're going to take.
Or you can turn the problem backwards. You can say, okay, given any amount of code, what is the most complex can it get? And the answer is there in nature already. It is in video coding, the images. They already, when you're trying to compress that, that's what you're looking for, how much you could build on the previous thing. So if you build a architecture backwards to deal with entropy coding, then you have solved that high-speed video coding problem, and you can throw Windows in there easily.
Do you want a compliment code, or I can maybe
this is a question that kind of relates to both of your points about the architecture maybe not being suited for certain tasks, specifically things that are very serial and not, trivially parallel. Can you speak a little bit to, because the architecture that you guys described is MIMD and not SIMD. Can you speak a little bit to the advantages if we're going to kind of compare this to, let's say, an NVIDIA GPU where you have SIMD and yours, maybe for example, for the advantage that you get, let's say, for pipelining neural networks.
So the real point of when you have a MIMD architecture is just that you can exploit task level parallelism that GPUs simply cannot do, or NVIDIA GPUs with the the current CUDA core and SMX unit, et cetera, architecture. That's a much longer question than the minute that I've got left. At a very high level, I would say that the biggest thing is just that compared to SIMD architecture, where you have 192 CUDA cores for each unit that are all restricted to doing the exact same instruction simultaneously. Each one of our cores have 4 execution units, all that can be doing simultaneous work, and then we have n number of cores on a chip that can all be doing completely independent tasks. The pipelining aspect, either in the case with our test chip, where we have 2 SerDes, or in the future having multiple SerDes covering all of the corners. You could do cool data flow or systolic array type things where you have big input data streams coming on one side and you're pushing across, or there's plenty of different models which you could take, either having a group cluster of cores operating and passing data together, where they actually are using the problem size that you actually have, the data is too large for a single core Scratchpad. You figure that it's actually worth taking the latency penalty to having to move and either square or a row of cores. And so that's very application dependent. Specifically on machine learning that you said, I've had a lot of people say that, is your architecture neural inspired or something? And I would say no to that, but the way that you do convolutional neural networks with big giant dense matrices and do matrix multiplication like that, you can do that on our architecture. I would say it's almost it's certainly more efficient than what you're going to get with a NVIDIA GPU, but performance-wise, a SIMD architecture can do really dense, large matrices pretty darn fast.
Basically, similar. That's his basic. Main issue is just the back propagation. So it's like a backwards FFT where you're sending all those coefficients.
I would say the training aspect, GPUs would have the performance advantage. The kind of like excuse me for the word, the actual running of a trained neural net afterwards would be something that I think we would be able to do very well, because you can have a group of cores dedicated to that, while other cores could be running different parts of your overall application, since that probably isn't the only thing that you want your chip to do. And that's just something a GPU wouldn't be able to do.
I'm sorry. I think you already have some of the answer there. Basically, FFT is a full butterfly.
Yeah.
And neural nets can be, you don't have to have a full butterfly, you can have just a small, levels of how you're switching backwards for back propagation. Not every node has to propagate to every previous hidden node. So you already have a neural net solution in your architecture.
Yeah, there is. I guess I'm skeptical. Well, I would love to be proven wrong and have my architecture be better, but I am holding out until we have real benchmark data. And I was really hoping we would have a couple more demos than just this one that I swear was running on hardware 4 hours ago.
So assuming that you are very, very fast with FFT,
yeah.
Right? I mean, given the convolution theorem and everything, and the convolution theorem, right, where you can just do multiplication after, in the frequency domain, but B, more specifically that backpropagation specifically can be rephrased as a convolution over the output from the previous layer with with the flipped kernel. So you can rephrase backpropagation as just kind of the same convolution. Theoretically, you should, if you're going to be as fast and as efficient for FFT, I can't see it, unless I'm missing something with the memory aspect there. It seems like you should be also very, very fast for at least convolutional neural networks.
Oh, I definitely think we'll be fast. I guess like our advantage compared to a GPU can't do an FFT like we're doing. It like our 16 core thing here, little tiny chip, will outdo a lot of NVIDIA's GPUs on just that raw level like that. I would love to actually have a benchmark to show that we can beat out, a GPU on.
The reason I asked about the memory subsystem was two-dimensional